So I too am very happy to be here at the occasion of the Tohoku Forum for Creativity. I am going to be discussing the Higgs, and I want to start by saying that in both Atlas and CMS, the two all-purpose experiments that announced the Higgs discovery last July, the activity on the different measurements and studies for the Higgs is at an all-time peak. We are now at a shutdown, but we produce results weekly that are new and studies that are new regarding the Higgs, but also we have started really introducing the Higgs in all the beyond the standard model searches, including SUSY. So we have SUSY, Higgs-aware SUSY searches and exotic searches. I wanted to thank also Hitoshi Yamamoto. Professor Yamamoto invited me here, and also I wanted to say that he taught me also high-energy physics at Harvard. I think my first graduate course in experimental particle physics was by Hitoshi. Now, as I was on the plane from Los Angeles, they gave us the Financial Times, and lo and behold, the centerfold for life and arts in the Financial Times was about the Higgs and the physics to come, and what they called the new physics. Which was a very extended section about the LHC, but not only about the LHC, and that impressed me. It was making the connections with cosmology, astrophysics, the data from Planck, and it was even going a step farther to talk about the other puzzling observations and theoretical considerations in physics today, such as graphene and quantum computing and quantum information and so on. So we have come from obscurity, let's say, in terms of pop culture, into being discussed normally right now. Then I turned the video, and what I saw was the wormhole with Morgan Freeman, my spokesperson, and Joel's postdoc at Fermilab explaining again the mysteries of beyond the Higgs and the Higgs itself. So the case was not like that 20 years ago when we were traveling and we said to somebody that we are particle physicists, and they stopped the discussion immediately. Here is the schedule. We are here now. Close to 2014. We call this long shutdown 1. It's going to take a little longer off the record, so we're going to be a little bit into the 15 when we will be on shutdown. The shutdown was because we need to upgrade the LHC and fix it from the accident that happened when we started taking data initially, and I'll show something about that. And so that we go to the energy, the specification energy of the LHC. You see, in the past 2 years, we are running at half the energy, and a little over half, so 7 TeV and 14 TeV. And in order to go into the energy that was originally prescribed, we need to fix the LHC, the superconducting cable connection with splices between the superconducting magnets. In addition, we're going to run at the nominal 25 nanosecond bunch crossing, and we're going to go into a little higher than the nominal, than the specification luminosity of the LHC, which was already the case in what we call run 1. Further to that, as we get into 2018, we're going into a new era where we are going to go into what is called after the completion of the phase 1 of the LHC, we're going to start preparing for the phase 2. And here there will be a phase where we take data with very high luminosity, and we stay at the energy of the 13 to 14 TeV, and prepare also for the very high energy LHC. In other words, work on the magnets in order to achieve something like between 30 and 35 TeV. So this is taking us down in the future to 2020 and 2025 even. It's a long program, and a lot will depend on what is going to happen here as we are collecting the data of the high luminosity LHC, which is the bridge to this era here. And I want to remind people that the way the LHC progressed was also with the accident and with how we evolved. We adapted to the conditions. It wasn't according to specification. And this is something that it is a valuable lesson in that we recover, we adapt, and we still did very well with the discovery. Here is just to give you a sense of the geographic area. This is Lake Geneva. The LHC is on the French-Swiss border. And we've got two detectors that made the discovery of that announced the discovery of the Higgs, Atlas and CMS. And we've got a bunch of other programs in the Collider, but also fixed target program at CERN. What I wanted to say is that Atlas is Swiss and CMS is French, and you can infer from this the sociology also. The little coins that passed by here was found when we built the CMS cavern, and it was Caesar Roman coins. So a lot of negotiations and financial exchanges were happening there between at those times. This is the tunnel, and these are the 14.5 meters superconducting magnets. On the front of this talk, I had on the very left side the dual core aperture magnet, which was invented in Brookhaven in 1970 by John Blewett. It was proposed for the LHC, but wasn't accepted. And immediately when the SSC was cancelled, the LHC adopted the technology, and it has worked really fabulously. The important part about this magnet technology is that in one magnetic enclosure, you have two beams of same sign particles going the opposite ways, which is highly non-trivial to achieve. This is the housing, this is where the magnets are, the housing of the magnets, and you see surfaces here. And I'm going to show you now that there's another beam line here, but it's not the beam line of the particles, it's all the cryogenics, it's the helium, because the magnets operate at 1.9 Kelvin. So the entire tunnel of the LHC is instrumented with another beam that carries the helium that enters the magnets there. So it took a lot of years. We started in this century. We started with this type of accelerators, with the 11-inch one that you could hold on your hand at Berkeley, and we have arrived through a lot of work and many breakthroughs, including the past century, the colliding beams, and the superconducting magnets, to arrive to the point that we can actually make discoveries like the top quark and the Higgs. It is highly non-trivial in terms of the technology on what has happened in such a little time for the human history in order to achieve that. The next step, the continuation of this program, and the next steps are really on the hands of all of the people today who are pursuing very ambitious projects like the ILC, and beyond that, pursuing the high energy frontier. So we had a bunch of conferences last year that were titled Higgs Quo Vadis, and after the discovery in Stockholm, where Mr. Higgs is going to get the Nobel Prize in December, I think. And this was the quote of the Nobel Foundation for the theoretical discovery of a mechanism that contributes to understanding the origin of mass of subatomic particles, which was confirmed through the discovery of the predicted fundamental particles. So, in fact, it's for the particle. This Nobel Prize is given to Higgs and Angler for the particle. And if one wants to consider how many Nobel Prizes the Higgs mechanism has received, it's a couple. One was given to Weinberg for including it in the Standard Model, because the Standard Model included the Higgs mechanism. And of course, the Nambu-Goldstone mechanism is the prerequisite for the Higgs mechanism. I think Joe will cover the history also on how all this was achieved through condensed matter physics and trying to do symmetry breaking in the vacuum, not only in complex systems. So Anderson, Goldstone, Nambu, all these people have thought about the Higgs mechanism back in 1960. That is a slide from before we started taking data. I think I was giving the slides in 2006-07 on what was the scope of the LHC. In fact, I had put them not in order, in any order of particular significance, but it is, of course, the LHC was built in order to find the Higgs particle, and so was the design of the SSE. This is a checkpoint here. We did find something like this Higgs-like particle. And so there is many other questions that we're asking ourselves in the LHC program and in the high energy physics program, and these include, David had them in his slides also, but these include, and not just the dark matter of the universe, and whether we have some additional space dimensions of this, or whether additional forces which would change the way we think about space-time. So now here is an overview of the bosons we have. So we have for electromagnetism, we have the photon boson, and then for the weak nuclear force, we have the W and the Z, and then we've got a bunch of gluon bosons for the strong nuclear force. These are all spin 1 bosons. And then we've got, I will call it the H boson for the moment, and this is the one that we think we discovered the particle at the LHC. We are confirming it. Now, when we say we're confirming it, it means by, first of all, excluding a lot of other possibilities of what kind of other particle that would be. It's not yet, we don't have yet the exact, all the measurements that are necessary in order to characterize it. So this is the first particle that we have with spin 0, and so it's a first new type of fundamental particle since the photon and the electron. The photon was a spin 1 and the electron is a spin 1/2. I'm not going to talk a lot about the symmetry breaking, the electroweak symmetry breaking, other than saying that when you have a symmetry in your equation, in your theory, and that you don't have in the solution of the equation the same symmetry, it appears that you have a mechanism that the symmetry is broken, but the natural solution, the realization, is what is happening. And so we have many cases of symmetry breakings in condensed matter physics, phonons, spin waves, and in superconductivity too. So I think Joe will cover all that. But what I wanted to say here is that the Higgs, in a sense, was kind of a natural consequence after experimentally, because we had already observed the W and the Z, and so the Higgs, the W, the Z, and the photon are part of the same story of symmetry breaking. Now, this is the symmetric configuration here, where all of this would be 0. This is the broken one, which is the one we observed with a measure with the W and the Z that have masses. The photon remains 0 mass, and then the Higgs boson, whose mass is determined by, in this Mexican hat kind of picture, by how steep the turnaround of the Mexican hat is. This one, okay. Now, if we didn't have something like the Higgs, one thing to note down is that then the mass of the W would be 80 plus infinity, so it would be nonsense. When we have the Higgs, the mass of the W is what it is, plus what we predict it should be, plus the logarithm of the Higgs. So there's something to be said about the connection of the W with the Higgs. And then there's one more thing to be said, and I think also Joe will cover this better or in depth, with what's going on with the top versus the Higgs. And so this is what I call the W-Higgs top triangle borderline disorder. In these three graphs here, this is the mass of the top, this is the mass of the W, the mass of the top quark, and the lines are giving you the mass of the Higgs. These look like the supernova measurements for those of you who are in cosmology or astrophysical measurements. And you see that we haven't yet arrived at precision in the masses of the top and the W and the Higgs that we have right now in order to figure out if this picture is consistent. Within errors it is, but we are within errors. If we look then at this plot here, which has the top mass here and the Higgs mass here, this is a picture that is telling us that the vacuum of the universe is not stable, it's rather metastable. And what this means, Joe will explain better, but it is a borderline situation to be in this kind of corner for the top mass and the Higgs mass. The way we say it is that if there's no new physics, then the universe in 10 to 100 years will tunnel into a new vacuum that will be more stable. And of course, to anyone with some common sense, this sounds like nonsense. Also, the 10 to the 100 years, there's something wrong with this kind of very big numbers and predictions. So we need to have the measurement, both of the Higgs and the top, with very high precision. In addition, this mass of the Higgs that we have, well, the 125 GeV was a mass for the Higgs that was chosen for the ILC studies. We didn't expect at the LHC to find 125 GeV, but we do have many studies for SUSY with the Higgs at 125 GeV. And this is a borderline between what is natural SUSY and unnatural SUSY. David and Steve mentioned a little bit about naturalness, and Joe will talk more. But again, it seems that we are like in some borderline situation here, where if it was a little less, it would be natural. If it is a little more, it is unnatural. So it's on the border here. And in other words, to say it's a little too heavy to be SUSY, it's a little bit too light to be strong dynamics. What is going on? This is, I think, these three plots here are the symptoms of a disease that your president would cure with the ILC, definitely, I think. Now, if electroweak symmetry was not broken, as in the standard model, and again, this was mentioned in the context of the discussions before, chiral symmetry breaking by QCD would break the SU2. The W and Z would get tiny masses, quarks and leptons would be massless, mesons and baryons would form, so the proton would be formed, but because of QCD, but they would be heavier than neutrons and they would rapidly decay, and so there would be no atoms or chemistry. So this is a slide actually that was given in some school from a Dutch physicist at Fermilab, where he said, he was a postdoc then, and he said when the Higgs is found, that was in maybe 1996, he said when the Higgs is found, don't say it's just a particle, it's a step towards a radically new view of our universe, and I think I'm convinced this is correct, especially because I was educated in a place where the Higgs was not taught as part of the standard model, really. There we are in the particle data book. It's there. Higgs bosons. This is in the edition of 2013 from July. This is the signal strengths in different channels. So we see channels in the combined ones. Signal strength 1 means that it's the standard model. And we've got here WW, ZZ, gamma, gamma. Still, it is higher than the standard model. BB bar and tau plus time minus. These are the ones that made it for the PDG. I want to say that we have many more channels where the sensitivity, in other words, what we expect, is the one type standard model, but we don't, if we were making a search, an honest to God search, we don't have 3 sigma for evidence or 5 sigma for discovery in individual channels. So many of the measurements we are giving when we say the Higgs looks like the standard model Higgs are without having discovered it in the particular channel, but by doing very good combination of all the data we have, which is good because this gives the statistical treatment is good, but also we have to put it as a caveat that we need to discover it in all the channels in order to do the characterization. And so this is expressed here in the particle data book, where it says possibly seen and possibly seen, while in these it's closer. The signal strength is closer to what you what you expect from the standard model, and the discovery also. That's why it says seen. Now there are some other limits here for the H classes in the context of supersymmetry and so on. But this is the first entry in the particle data book of the Higgs. Now, this creates a lot of questions, including this borderline disorder that I mentioned with the W, the dot, and the Higgs. There are many questions if there are additional Higgses, if there, as is expected in the case of supersymmetry, if there are other high mass Higgses. Also, if it is a mixed type of state and not a pure pseudoscalar or a pure scalar specifically. The pure pseudoscalar we have excluded with high confidence level, but that doesn't mean that the data says that with a high confidence level it is a scalar. Not yet. So for this type of measurements, we need a little more time. Here's again the LHC, and this is the tunnels that I was telling you feeding the cryogenics, the helium, and this is from 2005 when the detectors were just being installed. One in situ, Atlas was being installed in situ. I will show you that. And CMS was assembled on the assembly hall on the ground, and then it was brought down by a crane. It's 14,000 tons, so a special crane that is used to get ships from the Pacific had to come there, and we had to install it in order to be able to bring down the heavy pieces. So this is, I mean, we have the victory, and we celebrate the victory today and these years for the Higgs discovery, but we have to remember that this did not come without adversity or without times where everybody was disappointed or what is going to happen, etc. But in this kind of business, you do go through disappointment, and when you don't have prototypes and you commission something for the first time and there's no prototype, you sustain things like that, and maybe the reason, maybe you could have cured it, maybe you could have predicted it, maybe you would have reasons to prevent it, but there it is, it happened. And guess what, it took a year before we recovered and we went on with the program. And also it showed that with half of the energy we found the Higgs. So when we used to say that the Higgs is around the corner, it was really closer around the corner than we initially thought. If we turn now in 2015 or thereabouts, and we see a bunch of phenomena, new phenomena, all these people who are pessimistic and they say, well, there is no SUSY, there is no nothing, they would probably admit that of course we expected it, it was around the corner. So I think it is premature to have this sentiment overstated. I think it's good to be patient. Keep in mind that we did run at half the energy. We had a big accident and we did run at half the energy. And we recovered and we had a discovery. Here's now a little animation of the site in the LHC, and then we're going to go underground in the cavern of the Atlas experiment, and we're going to see the in situ within 2 years how they installed their calorimeter here. This is a fantastic calorimeter that I will show you results that nailed very much so the Higgs in the diphoton scenario, and these are the toroidal magnets of Atlas. Atlas and CMS, when they were designed back in the day, they were designed to be able to discover the Higgs in the decays, in the golden decay, to 2 Zs. In their decays to 2 lepto-Z, specifically 2 muons. So the final state they were designed to do the best was 4 muons. And for each muon, the design was such that between the 10 GVPT of the muon and the T VPT of the muon, you would have resolution that would be at the 10% level. At CMS, we have achieved a better, something like 6%. And this will be apparent when we see the results. So this drove exactly how differences of how the Atlas and CMS detectors are. So the detectors are actually dual. They have very similar performances. You will see from the results that the Atlas calorimeter outperformed the CMS, and that the CMS muon and tracker outperformed the Atlas. And so it seems that all balance in the end is among the two. Now, there's something to be said about this type of experiments. They involved a lot of people. CMS has about 3,300 scientists, technicians, engineers, and so on. About 900 of them are PhD students, and we've got 193 institutions in 40 countries. This is an example of literally international science at its best, and I think the example of these collaborations is a very useful example for how this type of science is going to be happening everywhere, including in biology and astronomy, where right now big collaborations are forming, interdisciplinary collaborations are forming. I think Andy was explaining to me that the word fusion in your university is interdisciplinary collaboration. So here we do have a lot of fusion of this type among people collaborating. So this is 1999.5. So the cavern of CMS was delivered in 2005, and that was about 6 years before that. When we started digging, this cavern had to be built for one of the 2 experiments. Atlas had the cavern already, and we had to freeze a river at -23 degrees and seal it. And the engineering was a very tremendous project that had to be done. You see, in 2005 it was almost done, and this is the service access. And here you see the CMS logo. On top of that, we had the assembly hall where the detector was assembled, and then piece by piece it was brought down. What we see here is the very forward part of the detector, which is the hadron calorimeter, and we see on this side we see the muon chambers. Here it is. This is the CMS stands for compact muon solenoid. The detector I showed you before was Atlas, and it had a toroidal magnet. This is a solenoidal magnet. It's 3.8 Tesla with a 6-meter freeboard diameter, holding with a current of 20 kiloamps because it's superconducting, and the stored energy is 2.7 gigajoules. So this magnet also didn't exist before we built it, and so the prototype and what we commissioned was the same thing. And no second of this kind of magnet exists in the entire world, although you may have heard that in medicine they use very high field magnets, but not with this kind of diameter. So this is unprecedented. CMS is 14,000 tons, and it's 14 pieces. The heaviest piece is 4,500, that includes this solenoidal magnet, and it was brought down piece by piece, modularly down. So this is a cross-section as a particle from the vertex goes through all the onion structure of the different detectors. In here you've got 100 million channels of silicon, that's like your camera, and 12 layers of this, the pixels and the silicon detector for tracking. What you have here is lead tank state, a calorimeter, that the design of which was determined by which kind of magnetic field you had. So you see, in very short length, it had to capture the shower of very high energy electrons and photons. So this was a very challenging thing to find a material that could do that. This. You see here a brass plastic scintillator, brass absorber, plastic scintillator calorimeter. It's a hadron calorimeter. And here I will show you something. I don't know if you can see it, but this is part of our DMS collaboration. This is Navy shells from Russia made of brass, because we couldn't, well, when we were trying to figure out how we are going to make the brass absorber, the brass is expensive. It's 1.5 times the aluminum, and it's even more expensive than steel. So what we did is we melted all the shells that were held by the Russians from the 1940s, and we made the hadron calorimeter. Again, it shows you how international collaborations work and what kind of really strange issues you solve with a bunch of people when you are even in dire straits with money and so on. It was a very innovative way to do this. And then out here you've got the muon chambers all the way out. So here you capture your charge tracks, you capture your photons and electrons here, you capture all your hadrons here. Although the hadrons do start, the first part of the shower of the hadron is stopping in the electromagnetic calorimeter. So for jets of 20 GeV, for example, you will see them starting and almost completely captured in the electromagnetic calorimeter. And then you've got muons from tracking and from the muon chambers. This is a nice picture where you can see the solenoid, the tracker being installed in here. The calorimeter, the electromagnetic calorimeter is in between the tracker and the solenoid, and the hadronic calorimeter outside, and part outside also of the outer hadronic calorimeter is outside of the solenoid, and then here are the muon chambers. Here is a view from piece by piece when we were bringing it down. This is down in the cavern, and you see here were the structures, the hangs that was hung from the crane to bring it down. And some other pictures when the detector was unbuttoned from before we entered for the first data run. Again, the superconducting solenoid. This is when it was brought down from the access cavern. So beautiful pictures of CMS at that time. Right now the detector is unbuttoned also because we're shut down, and so we have some access to repair some of the front-end electronics and some of the DQ also. This is Lynn Evans, and this was the day that we took the first collisions, and we were all happy and tired. And in 10 days, there was the big accident. Further to that, then I jumped here, and this is a picture when, in fact, this was the first high-energy collisions at 2.7 TeV, so we had surpassed the Devatron. We were celebrating. It was in the middle of the night, and I was the coordinator for the shifts, and together with Anders from Cornell, professor from Cornell, and we called in the middle of the night our spokesperson who came there. What we did is we turned on the entire detector very carefully, and we took first data before Atlas. So we were the first ones to get the high energy data. We were very competitive back in the day. I'm gonna say here one thing that for the standard model to be established, we didn't need to measure all the particles, but it took many years to arrive to the top and find the W and the Z bosons and measure them. It took a program that it was half a century, and if you want to go back in the day of cosmic rays and nuclear physics, it's even more. With the LHC, we went very fast. In 9 months, we had redone the entire discovery of the full standard model. This is Professor Higgs. Here he's in Atlas, and here he's in CMS. He was this is before we found the Higgs, so he was visiting already then because I guess he was sensing what's coming, namely his Nobel. there was decades really of Higgs hunting. So this is all the different exclusions in slices of the mass of the Higgs. And even Atlas and CMS, the first 2 years, they were excluding. And there was a little tiny corner here that was left, a little tiny slice. And it wasn't only decades of experiments, but also decades of calculating. And here's your supermodel theorist that is posing in all the pictures of theory and calculating for many, many years. I want to mention one thing about the data. It's 1 petabyte per second that the LHC is collecting, so it's hugely more amount of data than Google is handling. And this is the picture of the luminosity from 2010, 2011, and 2012. This is where the Higgs was announced. The amount of interactions per crossing that give you the pileup, the additional interactions, is shown here in vertices. So even the gold channel events, they have a lot of more vertices, but we are able to reconstruct them. Okay, so this is the first observation published, and this is Peter Higgs. We announced it on the 4th of July. This is Peter Higgs in August, sending us a message of appreciation. And this is for the US. This is from the White House. We got a thank you and congratulations note, and it was actually faster than the note of Professor Higgs. Theory meets experiment. This is Fabiola Gianotti, the spokesperson of Atlas, and your president said that indeed she was the #5 person in Time magazine. And now I'm going to go and describe a little bit the mass measurements for the Higgs, and a little bit beyond the standard model. I will run 5 minutes, I think. Here is the different channels of production at the LHC. The gluon fusion is the one that it is the highest, the dominant production, at 125. And then the subdominant production mechanisms, but with larger signal to background, is the VBF, which is 13 less in grade, is the associated Higgs production with W and Z. We call it VH. This is 18 less. And then associated TT by Higgs, 150 less. All of these have access to couplings, and we need to observe them in order to make couplings measurements for the LHC, for the Higgs at the LHC. This is saying the same thing, but all I want to add here is that we have gone a long ways in order to make calculations for all these. And so you see here next to leading Gordon, next to leading log, electroweak, and QCD corrections. The calculations are shown here, and these are the uncertainties. So we didn't have this back in the day. This is a big progress, and there's 2 large volume reports on these calculations for the Higgs. Here I show again the different modes of the decay, and all of these modes of the decay, mu, gamma, gamma, you see the relative ratio of them. So as a function of the Higgs mass, 125 is somewhere here, in a borderline case where you can start seeing it in ZZ and WW, and we saw it first in gamma, gamma, and ZZ. And here it's the same plot, but going all the way to 250. So with these different channels, we have access to measuring couplings. For example, Yukawa couplings for the fermions, the gauge boson couplings for the bosons, loop couplings for the diphotons because it goes through a top loop, and then gauge boson couplings for the ZZ, and Yukawa couplings again for fermions here tau, which are the ones that I showed you also from the PDG. So I want to remind you here, high energy, but not as high as we initially had in the specs. High luminosity, much higher than the specs. That means more radiation damage. And this is why the time that we have now during the shutdown is important to understand a little bit the recovery for the different detectors. And then very high data rates, so our computing issue and our triggering issue is something that we can tinker, but there's a lot of technology involved in that. Yes. So here is the discovery in that photons as a function of time in the Atlas detector. And you will start seeing, as a function of time accumulating data, you will see this little bump here. This was with the 4 0.8 inverse femtobarn from November 3, 2011, and then from December 9, 2012, the additional luminosity that was carried. This is the little axis. And here's the loop couplings that we were mentioning before, the Higgs going to the two massless photons through the top quark. The mass measurement for Atlas, for CMS, it's challenging because the CMS calorimeter, the lead tungsten CMS calorimeter, performed less than what we have expected, and we think it's because of the high radiation dose and the high luminosity, the instantaneous luminosity. This is the measured mass of the Higgs, 125.4. Statistics is 0.5 and systematics is 0.6. What I want you to notice here is that we are systematically limited here, not statistics limited. This event has two photons, but also it has two jets. These are the two jets. So this is the VPF Higgs mode, where you go to the photons plus jets. And we had enough fluctuation on this mode that gave us early on a higher rate for the Higgs to gamma gamma than expected. It made a lot of theoretical papers that the rate is a couple of times more than what you expect from the standard model. And now it has gone down to what you expect from the standard model. This was a real event. This is a real event with the two photons and the other deposits in the detector, the CMS. And here is the Atlas one, a stabler calorimeter. The pointing has helped them very much, the resolution very good, and they measure 126.8, 0.2 statistics, 0.7 systematics. Again, here systematics limited. You see here the peak a little cleaner. The golden channel is the channel that I told you both detectors were built for. Is the 4 lepton channel, and specifically here we've got in all 3 final states, so 4 muons, 4 electrons, 2 electrons, 2 muons. It's a very clean, closed, fully reconstructed mass with a high resolution. These 3 channels, this one I call the same, 2 mu to E, 2 mu is the same, 4E and 4 mu, and you can use the Candle mass in order to do the selection. It has low signal rates, but it has very also low background rates. This is why it's called golden. And it has an irreducible ZZ star background, but it's very well understood from the data also. And some reducible background that also is very well understood from the data. I will show you now the CMS Discovery plot, which was actually June 14, 2012, before we announced it, when we opened the box. This is the standard model background. This is the internal calibration with a Z, where you have radiation from one lepton to a photon, and so the 4 leptons here make a Z, not a ZZ. This is the continuum ZZ from the standard model. These are the cuts that are making this region here like that. And if you didn't have a signal, you would expect to see what is the blue, but in fact you've got the Higgs there. This was a very convincing signal for those of us who were not very convinced by the photons. And here is an animation of this type of events. They have this is a 4 electron event with the towers and the tracking also information, and this is a 4 muon event with only the muons. This is one from Atlas, which is a pair. Okay, so from Atlas, the measurement of the mass gave 124.3. This is the statistical uncertainty and the systematic uncertainty. So this is statistics limited. They will do better with statistics. They did an analysis that is more classical and conservative. This is the CMS analysis. The CMS analysis went a little bit on doing more let's say, adventurous stuff with the kinematic discriminant, taking into advantage all the configuration of all the angles, of all the decay products, of all the Z's and their decay products and muons. And so what we also did was an event-by-event mass uncertainty, and this helped improve up to 10% actually the mass uncertainty. This is why you see here the likelihood is much thinner. and we've got the best actually, determination of the Higgs mass at the LHC. I'm not going to say that, but this is what I was pointing to. The Higgs to 4L in CMS provides the best measurement of the Higgs mass, and you see the systematics here is very, very small compared to the statistics, so we are only statistics limited, and we have a long way to go in order to get a precise determination here. Since I don't have much time here, I will only say that with all the decay information, we really can do very well in determining characteristic properties. But so far, what we have done is we have excluded the pure pseudo-scalar case in favor of the scalar case, but we haven't. It doesn't mean that the data at 100% agrees with the scalar case. So the characterization measurements are ongoing. There are very many, and they are ongoing. And for these characterization measurements, we also stop now doing hypothesis testing, but we're going to do the full determination of the tensor structure, the Lagrangian and true precision measurements on all these, which leads the analysis from a one-dimensional analysis or a three-dimensional analysis to an eight-dimensional fit. So we will measure all the parameters, rates, and interference at the same time for all the tensor structure of the scalar. Having said that, this is also what David showed. We've got here the best fit for standard model strength for a bunch of channels. Now, one of the things that you want to do with that is start doing searches for whether you have deviations for the couplings of the standard model. This is just beginning with having with excluding benchmark models essentially. And this is the one here is the standard model, and this is where the different kind of couplings are falling according to this decay rate. Well, so what does this mean? Does this mean that we actually have at the LHC the measurements of all the couplings? No, it doesn't. It means that so far we don't have significant deviation from standard model predictions within the uncertainties, and the uncertainties for all the channels are between 10 and 100%. So there's a long way to go. Here, this plot is showing the couplings as a function of the mass of each individual particle and its coupling with the Higgs. This is top, W, Z, B, C, and tau. This is for the IRC. You don't even see the errors here. This is what we have without having the discovery in each channel at the LHC. So without having a 5 sigma discovery for all these channels, what we get from the data, this is why you see very huge errors here. So it's going to take time for the LHC, but the studies back in the day for the IRC are showing that this will be immediately very useful. So the next step for the IRC, the plan is to provide the next significant step in the precision study of the Higgs boson properties. The LHC precision measurements will be in the region of 5 to 10%, depending on what kind of innovation we have, and the IRC will bring it below 1%. In addition, any deviations that we have at the LHC with these measurements will be probed at the IRC. So I think I will have to skip the rest of my talk, unfortunately, but I'm just going to say one thing. Let's see. Both in terms of SUSY and bump hunts for extra Higgses and for SUSY scenarios, they are all informed by the Higgs. So there is the searches that we do at the LHC right now in terms of the optimistic scenario, the one that David mentioned as an optimistic case scenario, is something like that, where you will have in all these decays SUSY production, you will have the Higgs, and you will have dark matter particles. And this kind of searches that are informed by the Higgs are happening in cases of dark bosons, including now the Higgs plus emissivity, but also in cases of bump hunt. So excesses, like the excess that we used in order to find the Higgs itself. So I want to say that the questions remain. Many questions. If the Higgs, the H boson that we find, does it behave as predicted? Is it more than one, and how many more? Does it have the standard interactions or not? And this is going to be the major long-term challenge for the LHC. SUSY predicts 5 kinds of Higgs bosons, and we will hopefully, as we turn, we can hopefully have access to new SUSY particles, including the additional Higgses. And of course, whether it is connected with dark matter and dark energy, and in which capacity is something that it is important. Joe will elaborate a little more on that. I wanted to say here again, in the context of the IRC, that we have a lot of power in terms of excluding or probing dark matter even at low masses at the LHC. But what you see here is the probability density for getting omega dark matter from LHC measurements alone, which is this potato here. And the combination of an LHC with the ILC is shown in this very, very good measurements. So the combination of the knowledge from the LHC will inform the ILC very much so in the case of dark matter. So the big questions are big and they remain. We mentioned them, many of them. The Higgs is the beginning of an adventure into a lot of physics that we still have to understand, and we shouldn't exclude that something very complex is happening. This is cocktails and blends of whether you can take Majorana, 2/3 of standard model, 1/6 of actions, add queen, etc., and make a model where you have leptogenesis, where you have all the problems solved. You ignore some of the hierarchy problems, you ignore some of the other theory problems, but you get something complex. And so we have the access to understand all of that, including the cases of the cocktails and the blends, because we have the machines, accelerators, beams, tools of discovery, and I think the future is the next steps are very exciting on all the fronts of how this science is going to evolve. So I will stop here.
Thank you very much.